Hi, good afternoon.
Oh, good afternoon.
Good afternoon, Ms. Mokshin. Hello, Junaid. Hi, Tolwani.
Hello, Professor.
Nice to see you. I'm sorry I had to cancel last week. It feels like a long time since we've been here. Okay, so let's see if we can remember where we were. So if you remember, we had started defining the notion of topological conjugacy, right? So in general, the notion of conjugacy in general. So we have two dynamical systems. Let me just review it, just make sure, I'm sure you've been thinking about it. But if we have two dynamical systems here, defined on spaces with certain structure, right? Then we say that F is conjugate to G. So F, sometimes we can write it like this, so they are conjugate. If there exists a map, bijection, here that maps all the orbits to orbits. Remember, right, this was the key point. We're matching up all the orbits. This is the concept of saying that two dynamical systems are the same if we can match all the orbits. So if there exists bijection H from X to Y, such that if you apply F and then you compose H, and then you apply, that's the same thing as applying H and then composing G. Okay? And then we said that we have various degrees of regularity of this conjugacy. If H is a homeomorphism, then this is called a topological conjugacy. Of course, this applies only if X and Y are metric spaces. If H is a C1 diffeomorphism, so if X and Y are differentiable spaces in which you can define diffeomorphism, then this is called a C1 conjugacy and so on. You can have any kind of Lipschitz conjugacy, any kind of regularity. It depends on the regularity of H. And depending on the regularity of H, you preserve various properties of the dynamics. So each of these conjugacies is an equivalence relation on the space of dynamical systems. Because you can compose, of course, if F is conjugate to G and you have a third system here and these two are conjugate, then you can just take this composition of H1 and H2 and you can create a conjugacy between these two. So it's quite easy to see that this is an equivalence relation. Right? If you have an equivalence relation, it means it separates your dynamical systems into equivalence classes, sometimes called conjugacy classes. Right? So what this is, how we approach this is by thinking of the fact that this conjugacy allows us to make big groups of systems that are conjugate and think of them as being equivalent. Okay, so it reduces the number of systems that we have to look at. So I also introduced this notion of, I started introducing, but I didn't finish the notion of structural stability. But what I'm going to do, rather than go back to that now, I'm going to come back to that in the middle of the class because I'm going to discuss first the first systematic technique for proving conjugacies. And I gave you one simple example in which we have an explicit conjugacy, but the most simple setting in which we can really discuss and think about what it means to have different equivalence classes is in the context of interval diffeomorphisms. right? So if you remember, we discussed the fact that interval diffeomorphisms have a particularly simple structure in some way, in the sense, at least orientation preserving. Let's focus for the moment on orientation preserving interval diffeomorphisms. And in particular, they're monotone, if you remember. This was one of the reasons why the dynamics is so simple. And they're monotone, so every omega limit is a fixed point, right? So really, you just have fixed points and orbits converging to a fixed point. That's what makes, it's the monotonicity of these maps, if you remember, that makes the dynamics particularly simple. Now, the fact that it's simple, the question is, does it allow us to in somehow group interval diffeomorphisms into equivalence classes? So if we take two interval diffeomorphisms, do we know if they are in the same equivalence class? For topological conjugacy. So there are some characteristics which we know are obstructions to topological conjugacy, right? So for example, we know that if we take this interval diffeomorphism here, and this interval diffeomorphism here, they cannot be topologically conjugate, right? Why is that?
They have different number of fixed points.
Exactly, right? So this is obvious that these cannot be topologically conjugate. What about if I change this a little bit and I make them have the same number of fixed points, but this fixed point is like this. Can these be topologically conjugate?
No, it's character of different. Character of third fixed point is different.
And why is that a problem for topological conjugacy?
The fixed point is not.
The fixed point in the upper right corner in the first picture is global attractor.
That's correct. So we will not give a formal proof here, okay? But you can see, if you remember, what is the dynamics of these points. So in this particular situation here, so we have one fixed point here, P, and if you take an initial condition here, then it will converge to this fixed point. If you take the other initial condition here on this side, it will also converge to this fixed point, right? So this fixed point is attracting, and the two fixed points on the end points are repelling, right? Points are moving away. Even if you take a point that is very close to here, it is moving away. And in this case, we have this interesting situation where you see this, you can kind of see what's going to happen because the graph here is above the diagonal, right? Which means that points move to the right, right? So if you think about what the graph tells you, the fact that the graph is above the diagonal means that the point x, its image is above the diagonal, which means that it's to the right of where it was, right? And this keeps being above the diagonal, so it maps here, whereas this is below the diagonal, which means that points are moving to the left, right? In these one-dimensional interval maps, you can deduce a lot of information by looking at the graphs. Here, they have the same number of fixed points, but both sides are above the diagonal, so if you take a fixed point here, it will be also moving to the right. And if you take a point here, it will be also moving to the right. So the omega limit set of all the points, so this is a point P, even if this is the same point P, then all of these points, the omega limit is moving to this endpoint, right? And all of these points, the omega limit is going towards P. So P is repelling from the right and is attracting from the left. But what is the most important point is if you try to construct a homeomorphism between these two, it will be impossible, which is a conjugacy. If you remember, the conjugacy preserves omega limits, the topological conjugacy, right? This is one of the properties, additional properties that you get. If H is a homeomorphism, then it sends omega limits to omega limits, which means that if it maps this point to this point, so every homeomorphism must map the endpoints to the endpoints, right? So if it maps this point to this point, then it must map the omega limit set of this point, which is this endpoint, to the omega limit set of this point, but the omega limit set of this point is here, right? So these two cannot be topologically conjugate. So let's see what other obstructions there are to topological conjugacy. Suppose suppose I draw something that is similar to this, but the fixed point is in a completely different position. So suppose something like this. This is the diagonal here. So the fixed point now, let me call it Q to show that it's a different fixed point. Ling, what do you think? Can these two be topologically conjugate? Does it look like there's a possibility?
Yes.
Think they are? Why? Or you think they might be? At least there's nothing obvious that says they shouldn't, right? There's no reason. The two basic things which we know are an obstruction to topological conjugacy are different number of fixed points. So these have the same number of fixed points. And preserving the omega limit set of points. And this looks like perhaps if we constructed such a homeomorphism, what should this homeomorphism look like? Clearly, this homeomorphism should map the point Q to the point P, right? Because homeomorphisms, which are conjugacies, must map all the fixed points to the fixed points. So it can send the endpoints to the endpoints, Q to P, and then it could send this interval here to this interval here, right? In which the graph is above the diagonal in both sides. And this interval here to this interval here, in which the graph is below the diagonal on both sides. So it seems that it may be possible to do that, right? So I'm going to show you this construction, in fact, to show you, we're going to prove the fact that they are. And to do this, I'm going to introduce a very elementary but interesting, quite basic fundamental technique for constructing topological conjugacies. But first, let's ask ourselves the question, again, about what we expect. Just a couple of minutes standing back and say, are we happy to think of these as the same, right? Because remember that the different topological conjugacies, they're supposed to give us some equivalence classes, some conjugacy classes which have some meaning, for us in some sense, right? And depending on the regularity of the conjugacy, we will get different equivalence classes. For example, if I asked you, we're going to show that these are topological conjugacies. If I ask you now, suppose we can show that they're topologically conjugate, are they C1 conjugate? Which information would you need to know whether they are C1 conjugate? Or if they have a chance of being C1 conjugate? Toluwani, what do you think? You remember what C1 conjugacy preserves some additional structure here? We talked about it just at the end of the last lecture, so we did not spend too much time on it. But if you have a C1 conjugacy, so if H is C1, it preserves even more structure of the maps. Do you remember what that was? I can't hear you. You're muted, I think.
No, I don't remember.
You don't remember. Rahama, do you remember?
No.
Eunice?
No, I didn't attend.
You didn't attend last time, that's right. Ruba?
The tangents are different.
The what?
The tangents are the differential.
That's right. So I will put it as an exercise, but I'm glad I asked because I didn't realize we needed so much reminding of this. So the additional, in some sense, the main features you should think of that depend on the regularity of the conjugacy is that if the conjugacy is just a bijection, then it just maps orbits to orbits, and it maps fixed points to fixed points and periodic points to periodic points. So it preserves the property of whether a point is fixed or periodic or not. If H is a homeomorphism, then it also preserves the omega limit sets, right? So it must map, if H maps this point to this point, and the omega limit set of this point is this periodic point, then H must map the fixed points or the periodic points to themselves. Now, if the conjugacy is C1, then it also preserves the derivatives at fixed points. Okay, this is a simple calculation which I did last time. I will not repeat it now. But this means that if we could construct a conjugacy that was C1, we could only do that. We haven't proved yet that we can do that, but if we were able to do that, it would necessarily mean that the derivative at the corresponding points are the same. So the actual slope, this is what Ruba was saying meant by the tangencies, right? The derivative, the tangent, the slope of the graph here should be the same as the slope of the graph here, exactly the same. The derivative at this point P should be exactly the same, and the derivative at this end point here should be exactly the same. So you can see that the jump from topological conjugacy to C1 conjugacy is a very big jump, right? It's very restrictive. A C1 conjugacy means really that there's a lot of rigidity, especially at the fixed point, okay? But that was just an observation. Now let's think about how we're going to prove this theorem, that these two are conjugate, okay? And to do that, we're going to start with an even simpler case. So we're going to prove the following theorem. Actually, let me write this theorem. Following, we suppose F and G. Suppose F and G are interval diffeomorphisms. So C1 interval morphism with same number of fixed points. Okay, and such that C1 hyperbolic, sorry, C1 hyperbolic interval morphisms with same number of attracting and repelling fixed points. Okay, like in this case. So what we mean is that they have the same number of fixed points, and they have the same, and the corresponding fixed points have the same, like here, these fixed points are repelling, this fixed point is attracting, this fixed point is repelling, and they alternate actually. If it's hyperbolic, so remember that hyperbolic means that every fixed point, so hyperbolic, just to remind for those of you who were there, means that the derivative at each fixed point is different from 1. For all fixed points. Okay, so you can't have this tangency situation. In particular, this means that you always cross the diagonal at every fixed point. You either cross it like this, or you cross it like this. So you may have something that crosses many times like this, okay, but you always cross it. You cannot have the tangency situation that we had. Okay, then F and G are topologically conjugate. In fact, this is if and only if condition, right? Because it's clear that if F and G are topologically conjugate, then they must have the same, if they're hyperbolic, they must have the same, well, in any case, they must have the same number of fixed points which are have the same number of attracting and repelling fixed points. So really, this is if and only if. This completely characterizes the conjugacy class by the number of fixed points. Right? The number of attracting and repelling fixed points. So any two hyperbolic interval diffeomorphisms that have the same number of attracting and repelling fixed points are topologically conjugate. So let's prove this for the simple case in which you have only just two fixed points, and then it will be very easy. I will leave it as an exercise for you to do the general case. But this allows us to introduce the technique. So let's suppose that we have just this picture here, and then this other picture will be just to let's do something like this just to show that they're not very much the same. Okay, so suppose first just two fixed points. So in that case, the two fixed points need to be at the two end points, right? So how are we going to construct conjugacy? We need to construct a bijection between these two. We need to construct a homeomorphism, right? So clearly we will send, we can suppose this is the interval 0, 1, just for simplicity in both sides, but it doesn't matter. So clearly we want to send 0 to 0 and 1 to 1. And then how are we going to define the other points? What do you think? So if I take some point here, x, how am I going to choose which point to map it to? How am I going to somehow construct a conjugacy that maps orbits to orbits, right? Remember, what we're trying to do is, in a schematic form, if you take a point x here and you apply f of x, right? And then you apply h to f of x, you want to end up in the same point that you get when you apply h of x, and then you apply g to h of x. Right? These are the same point. That's what this means. G of h of x is the same as h of f of x, right? So we saw that when you do this, if you have a bijection that maps, that satisfies this for all the possible points x, right? Then it also means that f of x, if you apply h to f of x and you get h of f of x, and you look at the next image, f2 of x, then g will map this to the point that you get when you apply h to h2 of x, right? So if you have this condition, you automatically get that all the iterates of fn and gn are conjugate, right? So that's why what this means, if we have just this condition without the n, it automatically implies that this conjugacy will map the whole orbit of a point to the corresponding orbit. If h maps x to some point h of x, then it will map all the points of the orbit of x to the corresponding points of the orbit of g of this point. This is the intuition behind the conjugacy, right? Then the regularity of the conjugacy is a slightly different matter in general. So usually, often, at least in this case, the first step is to construct the conjugacy, and then we will check that we can make this into a homeomorphism. So how can we do that? If we have a point x, this is going to map to some other point, h of x. Somehow, suppose we've chosen it. Let's call this y, y0. Let's call this x0, and y0 is here. Suppose we just choose randomly, we just choose arbitrarily some image. What constraints does that put on our map? The fact that we've chosen that x0, h maps x0 to y0 means that we have now no longer can choose arbitrarily for the other points, right? Which points are we now constrained that we have no choice for which to decide? What do you think, Milmukshin?
It cannot take boundary points. It might be in interior point, for example. This one, y0, must be interior.
That's right. Very good. So, as we said, h of 0, 0 will be h of 0, 1 will be h of 1, so we will map this. So now, if we hope to show that these are conjugate, we need to find some homeomorphism that satisfies this condition. So I'm kind of suggesting, okay, let's just try, we have all the points look the same here, right? There seems to be no other distinguishing feature. There's nothing we can hold on to. I mean, we could look at the slope here, but the slope could be anything. You know, you could have very different slopes here. It's not clear what that has to do with it. So let's see what happens if we just take an arbitrary point here, x0, and map it to an arbitrary point, y0, here. And then is there a second point that now has, the map H has to map a second point to to a second point. For example, x0 maps to x1 here. This is the image, right? This is the map F, this is the map G, F of x0. So which point should x1 map to by H? We don't know, we don't have the H yet. We are defining H as we go along. Where do you think the image of x1 should be? Can it be here? Should it be here? Should it be here? Do we know anything about what H, where H should map x1? Junaid, what do you think?
I think it should be towards the right of y0.
Why should it be to the right? Toluwani, tell us.
I also think it should be towards the right, but I don't know why.
Which point exactly to the right? Should it be here, here, here? What do we know? What is the conjugacy condition? What was the picture that I just drew here? x0, x1, right? y0. So this is our y0. So what did I say? If H maps x0 to y0, H of x, then f of x0 must map to which point?
Y1.
To y1, exactly, which is g of hx, which is g of y0, which we write as y1. Right? This is y1. So this is why I tried to draw this picture again, so you really get a feeling for this kind of diagram that we've got here, right? We've got 2 points. I'm trying to give you a feeling for what this conjugacy means, right? So this conjugacy means that if you have 2 points where one is the image of the other by F, then H must map both of these points to 2 points where this one is the image of this one by G. This is exactly what this condition says when n is equal to 1. So that means that if we're trying to construct the conjugacy, we must construct a bijection that has that property, right? So if you choose an arbitrary point x0, right, and you look at, under F, you look at x1, and then you choose, at the moment we don't have any reference point, so we don't know. So we're just trying things out. So let's just choose an arbitrary point y0 and decide that H will map to y0. But what I'm telling you is that now, as soon as we've made that choice, we can no longer choose the image of x1, right? So the image of x1 must map to the image of y0 under G. So the image of y0 under G is exactly here. This is y1. Is that okay?
Yes.
Yeah, please ask me if you get lost in something. I'm trying to really emphasize because I think it's so easy sometimes to take a definition and you look at it just purely algebraically or formally, and then you go and you prove things with this definition without really getting a feeling for it, right? But it's essential that you get an intuition for what this means about the dynamics. And the same way I want to motivate the technique that we're going to use for this result by showing that it's a very natural technique that really comes from directly applying the concept of this definition. Okay? So now that we know that H maps this, we also know that Y1 has to be H of X1, right? So we cannot choose it. So as soon as we've chosen one point that H maps to. We've chosen another point, and then we've chosen the whole orbit, right? So not only y1, so we know that x1 maps to x2, right? And here we know that y1 maps to y2. And so we know that if H is going to be a conjugacy, it must map x2 to y2, and so on, right? So here we have this infinite sequence of points that is converging. We have x3 and so on, right? And then we have y2, y3, and so on converging to this. So, if we whatever, at some point we're going to construct this conjugacy such that it maps one point x0 to some point y0. And as soon as we've done that, we no longer have any more choice about the whole image, also the backward image in backward time, right? So in fact, x0 also has a pre-image here, which is x minus 1, and a pre-image here, which is x minus 2, and a pre-image here, and it goes all the way back. And this point also has, so y0 has a pre-image, which is this point here, which is y minus 1, and this has a pre-image, and this has a pre-image, and so on. So you have here y minus 1, y minus 2. So you have the full orbit of the point in forward time when you iterate forwards, but these are diffeomorphisms, so they're invertible, so you can iterate backwards. So this conjugacy implies that once you fix the image of this point x0, you have necessarily defined the value of H in the full orbit, backward and forward orbit of x0. Okay? So how much freedom do we have left? Of course, the question is, can we now extend this to the other points? So could I, for example, just continue this way? You know, can I now just take some other x0 tilde and do the same thing? And then I just take x0 tilde, and then suppose I was trying to do that, okay? Let's suppose we're really exploring, okay? So how would I make a realistic choice of where H would map to? Well, we know that H maps, yes?
Between y0 and y1, because H is monotonic, must be monotonic. It's also continuous and interval homeomorphism, so it must be
Exactly.
monotonic.
Right? So what we're aiming for is we are hoping to find H to be a homeomorphism, right? And therefore monotone. So H will be a homeomorphism that sends 0 to 0, 1 to 1. So it will preserve the order of all of these, obviously, as we've seen, right? So H maps x0 to x0, it maps x1 to y1, and so on. All these have a certain order that it preserves, and it must also preserve the intermediate points, right? So it must map this interval x0, x1, it will map it to the interval y0, y1, right? And so if I take this point x tilde 0, and I choose, suppose, I don't know if I will have all this flexibility, right? But I'm trying things out. I'm see what happens. So suppose that I just choose an arbitrary point here, and I map it to some arbitrary point here, y0 tilde. Let me use a different color, actually, for this. So let's take x0 tilde, y0 tilde. So then, what do I know about the image of x0 tilde? So I know, again by monotonicity of f, that this interval x0, x1 is mapped to the interval x1, x2, right? Because x0 is mapped to x1. You can see it also in the graph, right? So this is x0 in the y. This is x1. This here is x2, right? So you can see x0 maps to x1, x1 maps to x2, right, which is this, and of course the whole interval x0, x1 maps to the interval x1, x2. Right? So in fact, the dynamics is already giving us some information here, right? So clearly this interval is mapping to this interval, then this interval is mapping to this interval, right? And therefore, of course, if I take some x0 tilde here, then the full orbit of x0 tilde will contain exactly one element inside each of these intervals, right? So the x1 tilde will clearly be between x1 and x2. x2 tilde, we don't know exactly where it is, but they will be here, and so on. This one will be here, right? So we will have one point inside, in between each of these intervals, and the same thing for here, right? y0 tilde, and then here we will have a y1 tilde, and here we will have a y minus 1 tilde, and we will have one point inside each of these, right? And so H can map the full orbit of x0 tilde to the full orbit of y0 tilde. Now maybe we can start seeing a little more systematic, something we can do a little bit more systematic. Does anyone see this? Because we already have some information now that this, all this interval here maps. So as we just said, this interval here maps to this interval here, maps to this interval here, right? So really, if we're trying to construct this homeomorphism, a natural choice would be to map all these points inside this interval to the corresponding interval here. So my question to Rahama, can I ask you a question?
Yes.
Okay. So if I take two different points inside this interval, x0 tilde and x0 hat, and I look at each of these has an infinite forward orbit that is converging to 1, and a infinite backward orbit that is converging to 1. If I take two distinct points, is it possible that any of its images coincide, or will the two orbits be completely disjoint? Did you understand the question?
Yeah.
Yeah. What do you think?
I think they will be disjoint.
Why is that?
Because since the map is bijective, I think they will be disjoint.
Yes, absolutely correct. Absolutely right. Yes. So the map itself, F, is a homomorphism. In fact, it's a diffeomorphism, right? So it's a bijection, which means that 2 points can never map to the same point, right? So if you take two distinct points and you look at their images, they will be distinct. Their images will be distinct, and so on, right? So if you take any of these any 2 points here and you look at their images, they will all be distinct. And also, there will be one of these images, because this is monotone and order preserving, then we will have, you know, when we chose the first point, x0, we created, by looking at its orbit, we created a kind of infinite partition of the interval, right? Because we started with x0, and then we have this infinite sequence of points going to 1, infinite sequence of points going to 0, and then we have these intervals between x0 and x1, x1 and x2, x2 and x3, right? So we have this subdivision into intervals, and notice that every point here will have exactly one point of its orbit will be inside each of these intervals, right? Because you can never jump one of the intervals because these intervals are formed by the images of x0, x0, x1, x2, x3, x4. And because this is order preserving, if you start with a point between x0 and x1, then its image must be between x1 and x2. Its next image must be between x2 and x3, and so on, and in backward time as well, right? So in fact, what we have here is that all of these points, any point you choose here, will have an image inside these intervals. In fact, this whole interval here, right, maps homeomorphically, except for the boundary points, right? The boundary points we'll see in a second, but if you forget about the boundary points, it maps homeomorphically to this interval, right? And this interval maps homeomorphic to the next interval, and so on. It fills up the whole interval, right? And its backward image will be this interval, and so on, this interval, this interval, this interval, this interval. Okay? So now, what do I do? Well, it's easy. All I need to do is map all of these points to this interval here. So I need to map, so let me call this interval here I0, right, this interval here. And this interval here, let me call it J0. So I0. So to resolve this issue with the boundary points, let me take it half open and half closed. So let me take it closed in x0 and open in x1. Right? And then let me do the same for J0. And let me define J0 is equal to the closed interval y0 and the closed interval y1. Okay? And now, let me define a homeomorphism H, or a bijection H, between these two intervals I0 and J0. Okay? This means that I decide for every point in I0, I map it to some point in J0, bijectively. Can I do that? Can I define a homeomorphism between I0 and J0?
Yes.
Yes. These are just two intervals, and there's plenty of homeomorphism between these two intervals. I can even take this homeomorphism affine if I want, right? Just by a rescaling. I can even take it just by a factor. I just take the length of this and I rescale by this. I can even take it with constant derivative. But it doesn't matter, okay? What's important is this is a bijection, a monotone bijection, so homeomorphism that maps x0 to y0. Because remember, that's what we wanted. Our H, we already decided that we need H to map x0 to y0, right? And now I'm saying, okay, take any homeomorphism that maps this interval here to this interval here. So now I'm going to ask the same question before. How much freedom do I have left now? For example, if I take, so suppose I've done this. So suppose I've defined this homomorphism. And now I say, okay, I take some arbitrary point here, x, and I say, okay, now this x, I'm going to map it to some y here. How much freedom do I have to choose if I want to, I'm trying to extend this h to the whole interval, right? So I've now constructed h, which maps the endpoints to the endpoints, which maps the orbit of x0 to the orbit of x0, and maps this interval to this interval. Now if I choose a point here, x, I want to extend this to a homomorphism of the whole interval, right? So I want to decide by some h that is consistent with everything, what is going to be the image of this point here? So how do I choose the value of h of x? What do you think? Ling, what do you think? Do you have some idea how we're going to decide, or whether we can have freedom or not? It's not an easy question, this.
I think the image has to be between y negative 1 and y 0.
Very good, very good. So if I choose it inside, so this would be I0, this would be I1, and this would be I2, say, right? So I2, oh, sorry, I minus 2. I minus 2 would be between x minus 2 and x minus 1, right? This interval here. So if I take a point x here, then you're saying that you'd expect the image to be inside j minus 2, right? Why do you think that should be the case?
Oh, I think it should be in j minus 1.
Excuse me?
I think it should be in j minus 1, not j minus 2.
And why is that? So this is j0. So here, okay, the picture has a little bit too much stuff on it here. But why should it be in j minus 1? So we know, so the general definitions, okay, so let me summarize, sorry, before we go on, let me summarize what we've done, right? So what we've done is we've chosen some arbitrary x0 in the open interval 0, 1, right? And we have let y, so we have, okay, choose x0 and y0 in 0, 1. So we started by choosing two arbitrary points, x0 and y0, okay? And then we defined h in this way, at that point, okay? And then we let h be defined by, so now we have h of, sorry, yk is equal to h of xk for all k in z. Right? So this is a definition of h, right? So we choose x0 and y0, and then we define h in certain points such that it maps x0 to y0 and the whole orbit here, right? And then we define ik to be equal to the interval xk plus 1 half open and half closed, right? So I0 is x0, so even for negative k, we have all of this. And then we have j of k is equal to yk plus 1, okay, for k in z. Now, what can you tell me about the union? What if I take the union over k in z of ik? What do I get? Are these disjoint, first of all these ik's?
Yes.
They're disjoint, right? This is an important point because that's why I took it half open here. So the image of this half open interval, x0 will map to x1, x1 will map to x2, right? So not only they're disjoint, but each one maps to the next one, right? And so we have, okay, let's first show that. So notice that, let's
Open interval. 0, 1 open interval. This
Exactly,
union.
exactly. So first of all, notice that all the IKs are pairwise disjoint. Okay, JKs are also pairwise disjoint, which means if you take two different Ks, IK and IK prime, they're disjoint. This is also pairwise disjoint. And the union of K in Z of IKs contains everything except the endpoints, right? Because this is really a sequence of intervals that is getting closer and closer to 1. This is a sequence of intervals that's getting closer and closer to 0. And the same for the JKs, right? This is equal to the open interval 0, 1. And this is the same as a JK. So this forms a partition of 0, 1. This forms a partition. And moreover, what do we have if we take the image F of IK? What do we get?
JK.
Not under H, under F, right? Just under F.
Just K plus 1, AK plus 1.
That's right? Because each of this image, so I0 maps to I1, maps to I2, and so on. So Fk is equal to Ik plus 1. And G of Jk is equal to Jk plus 1. Not only that, but F, maybe we should write it better like this. F is actually the map F from Ik to Ak plus 1, and the map G from Jk to Jk plus 1. These are actually diffeomorphisms onto their images, right? Because each one maps diffeomorphically to the next one, right? It's just this. So diffeomorphic onto its image. So I0 maps diffeomorphically onto I1, and so on, right? This is for every K. So we're almost done here. Can you see that we are pretty much finished here? Because now all we need to do is this step here that we did before, right? So now we define, let me, okay, so now we let, so here we define arbitrarily, so let H, let me call it H 0 from I0 to J0 be a homeomorphism. Okay, which is this homeomorphism here, right? So H from I0 to J0. So we map this interval here to this interval here. And now you see that from all this information that we have there, there's really only one way that we can extend this H to the whole interval. Because following the philosophy, I will write down the precise formulation in a second, but following the philosophy that we've just used, there's not much we can do, right? Because if you take, for every point here, what we said before is that if you decide the image of this point, then you have decided H, at the full forward and backward orbit of that point, right? So if we take x0 tilde and we decide to map it to y0 tilde, then we no longer have the flexibility to decide where we want to send x1 tilde, x2 tilde, x minus 1 tilde. It is fixed for us, okay? So now we just happen to have decided by defining this h0, the image of every point inside I0, right? So for every point inside I0, h0 is sending it to one point here, which means that we have no flexibility left at all, right? Because for all of these points, each one of these will have a full infinite or forward and backward orbit, and we will need to define our h in the way that is consistent with that, right? So we will need now for all of these points have full forward and backward orbits, and so we are determined. There's nothing else we can do really but define h. For example, on this interval here, right? If we want to define the image of each of this interval here, then we say, okay, what is the image of x1 tilde? The image of x1 tilde is going to be some point here, but I know that x1 tilde is the image of some x0 tilde here. So let me go and have a look at what h0 does. So h0 maps x0 tilde to some y0 tilde, and then I look at the image of y0 tilde, and it gives you y1 tilde, and then I say, okay, so the only possibility I have for the image of x1 tilde is y1 tilde, right? So I look at the pre-image of x1 tilde, I look at what point h0 maps it to, and then I take its forward image, and then I map those two. And in the same way, I take x2 tilde and so on, and I know that I don't have a choice. I need to map them to those other points, backwards and forwards. And since I've done that for all the points in these intervals, then I have fixed everything. So don't worry. I know that I've not given you a fully formal proof, but in the notes that I will give you and in the exercises, I will develop exactly the formalized version of this. Okay, here I wanted to build up. Rather than just give you the proof and the formal definitions, I wanted to really show how we get to it. Okay, so in the notes, I define the notion of a fundamental domain. So a fundamental domain on an invariant set is a domain on which every orbit spends exactly one iterate. So this argument that we have just done is based on the fact that every point on the interval, if you look at its full orbit, it has exactly one point in here, right? Because of what I wrote, because this is a fundamental domain, because the union of all its forward and backward images are all pairwise disjoint, and they fill up the whole space except for the endpoints. That means that if you take any point on the interval, right, every point on the interval will belong to one of these IKs, right? And since it belongs to one of these IKs, you can map it either by forward iteration or by backward iteration. You can map it to I0. Right? So every point belongs to one of these, and so some image or preimage belongs to I0, and once it belongs to I0, we have already decided how it's going to map to J0. Okay? So basically we extend that point. So we take a point, any point we want in this IK, and we say, okay, how are we going to define the map H in that point? You say, well, no problem. I now go backward all the way for say, 200 iterations until I end up in I0, if I'm in I200, okay? And then when I'm in I0, I know how to map it to J0, and then I map it forward by 200 iteration so that I end up in J200, and I look at the point that it belongs to, and that's how I define H from this point to this point. Okay, I want to take a quick break because I want to do something else. Let me just say that I will leave it as an exercise. So this this shows that it's a bijection. This shows how to construct the bijection. You then show that that H is actually a homomorphism. So there's a couple of steps missing, but they're not difficult steps, and it's better that you work on them yourself. And then it's very easy to extend this argument to if you have several fixed points. So let me, if you have a hyperbolic fixed point, two hyperbolic maps with several fixed points. So if you have two maps, okay, this has 4 fixed points. 1, 2, 3, 4. If this one has 4, even though they might be in different positions, okay? Then as someone remarked before, you can now do exactly the same argument on each piece, right? If you look at this interval here, and this interval here, and then the dynamics on this interval and the dynamics on this interval is exactly like the dynamics here and here, right? You can do exactly the same thing. So you divide the space into these 3 blocks in this case, okay? And then you can show that you can construct a homomorphism from this to this, and then you show that you construct one again from here to here, and then another one from here to here, and then you put them all together, okay? So I will put an exercise for you to check that, but it's really exactly the same thing. So the most important point about this is that we've constructed the fundamental domains, which means intervals which have this property that the unions are they're pairwise disjoint, their unions covers essentially the whole domain, and they map one to the other, and then all you need to do is construct a homomorphism between 2 elements, 2 of these fundamental domains, and you can extend this to the whole space. Okay, so let's take just a very quick break to have a glass of water, okay, 3 minutes, and I will see you back at 10 past 5. Okay, so let's just a short break today because I went a little bit longer. So I started introducing in the last lecture the notion of structural stability. So we can talk about it in the setting of interval diffeomorphisms. So this concept is very interesting, structural stability. And the question really becomes very natural once you have the notion of topological conjugacy, right? Because as we said, topological conjugacy is an equivalence class, and therefore, as soon as you've got an equivalence class, you can ask the question, okay, if I perturb my map a little bit, so let's suppose we take a map, an interval diffeomorphism. We stay in the world of interval diffeomorphism. Let's take let's take this interval diffeomorphisms. So my question is, if I perturb this a little bit, do I remain inside my equivalence class? Right? So the notion, the fact that the topological conjugate is an equivalence class allows us to formulate this question, right? So we can think more schematically that we have this world of C1 interval diffeomorphism. So we can say X is equal to the space of all C1 interval diffeomorphisms. The space of interval diffeomorphism. And then inside this space we have some equivalence classes, right? So we can think of a kind of, in some sense, a partition of the space, because that's what an equivalence relation does, right? So these are topological equivalence classes. For example, what we just proved is that if two interval diffeomorphisms are hyperbolic, so all the fixed points have derivative less than 1, and they have the same number of attracting and repelling fixed points, then they belong to the same topological equivalence class. So a general question now, if you perturb your map, do you remain inside your topological equivalence class? Or in other words, is your topological equivalence class open? Can you make a small perturbation and stay inside? This is the definition of an open set. But of course, for this, we need a topology, right, to make sense of this question. We need a topology on this. So there are various topologies we can define on the space of C1 interval diffeomorphism, and it turns out that they have different properties. The equivalence classes have different topological properties in here. So we can define, as I started defining last time, what's called the C0 metric, which is just this is just the maximum. So if these are compact intervals, then we can just take the maximum of f of x minus g of x over all x in I. And you can check that this is a metric on the space of interval diffeomorphisms. Right? What does that mean? This means that if you take a map F and I take a map G, so to say that if the distance between a map F and G is less than epsilon, this means that for every point X, you look at f of x, and then it means that g of x must be within epsilon of f of x, right? So this is f of x plus epsilon, and this is f of x minus epsilon. So this means that the graph of g of x must be somewhere between these 2 points, right? G of x must be here. And this is true for every point. So if you take another point here, right, its image f of x will be this, and it means that you have, now I'm drawing big epsilon, but of course you should imagine small epsilon. So that means that you have a kind of neighborhood of the graph, epsilon neighborhood of the graph. And that means that the function g should be everywhere inside this neighborhood, right? So I can, as long as I stay inside this neighborhood, this is g. And this means that if you take any point here, x, and you look at f of x, and you look at g of x, which is here, then f of x and g of x are less than epsilon from each other, right? And the same thing here. So this is what the metric, C0 metric, looks like. And you can see immediately that this C0 metric is very wide, right? So you can quite easily create more fixed points. Even if you take epsilon very small, so maybe I should draw another picture. So let me draw another picture here. Let me draw again the same f, right? Now let me take a very small epsilon, and is it possible, so suppose epsilon is very small, which means, let me just do it here, near here, okay? So if I have very small epsilon, it means I will define a function g, another interval diffeomorphism g, and the question is, can I take another interval diffeomorphism which is very close to f in the C0 metric, but is not topologically conjugate to f, right? This is the question. So can I move outside the topological conjugacy class with an arbitrarily small perturbation? So any epsilon you give me, can I find another interval map, interval diffeomorphism, which is not in the same topological conjugacy class? So the easiest way to make sure that two maps are not topologically conjugate is that they have a different number of fixed points, right? So the easiest way to do this is, can I construct a map G which has a different number of fixed points, okay? And the easiest ways to do that is to construct a map that has more fixed points, because if I take a small epsilon, some small epsilon like this, and let me blow up this because otherwise it's too small. So let me just draw it like this. This is the diagonal. This is the graph like this, right? And then you can see that small is, of course, just relative, right? So my epsilon is something like this, okay? And then all I need is to construct a map G which stays inside this region, okay, which means the graph is inside this region, and it's very easy to see that I can stay inside this region and I can easily construct more fixed points. Okay, so this map F and this map G are, if this distance here is epsilon, then the C0 distance between F and G is less than epsilon because the distance at every point between F and G is less than epsilon, but I can easily construct more fixed point. So that means that if you look at the space of interval diffeomorphisms with the C0 metric, okay, which induces a certain topology on the space of C1 interval diffeomorphism, well, I haven't proved it yet, okay, but you can see, you can believe from this construction that you can always create or destroy new fixed points, whatever you've got. So in the C0 metric, none of these equivalence classes are open. Wherever you are, you can have arbitrarily close to that some interval diffeomorphisms which belong to different equivalence class. Whereas on the other hand, if we define the C1 metric, so the C1 metric between F and G is equal to the maximum over all x in I of f of x minus g of x, okay, and f prime of x minus g prime of x. Now this gives a different metric, right? This says that two maps in the C1 metric are close if they are C0 close. So in other words, the new map has to be inside the epsilon neighborhood. The graph of G has to be inside this epsilon tubular neighborhood of the graph of F. But at each point, you also look at the derivatives, right? So you look at this point, and you look at the derivative of the map F, and you look at the derivative of the map G, and you say, okay, the difference between these two derivatives needs to be less than epsilon also, right? So if D1 of Fg is less than epsilon, this means that f of x minus g of x is less than epsilon, and f prime of x minus g prime of x is less than epsilon. So this is a more restrictive topology, right? So you may have some two maps that are very close in the C0 metric, like this one, because you see that here, this picture that I drew, here the derivative is much bigger, right? So here you have the derivative, the maps are within epsilon, and the derivatives are within epsilon. But here, when I tried to create the new fixed points, I had to really kind of change the derivative. If the derivative stayed similar, you can see, I'm going to leave it in the notes and as an exercise to prove this, but you can see that you cannot, if you were to keep the derivative fixed, you cannot kind of go up and across like that, because the derivative needs to be similar. And if the derivative is similar, you need to more or less go at the same speed. You can't suddenly do this, right? So, so these are very different metrics. One of them is stronger than the other, right? In this case, you have these two maps are very close in the C0 metric, but very far, very close in the C0 metric, but very far in the C1 metric because the derivatives are different. Which means that it's much easier to approximate a function in the C0 metric. There's many more closer functions. And the question is, what happens? The question is what I said correct? Okay, so is it true that I cannot do this? And the theorem is indeed that if f is hyperbolic, then it is C1 structurally stable, okay, by which I mean, i.e., I mean, there exists some epsilon greater than 0, okay, such that if the C1 metric, this is what C1 structurally stable between F and G is less than epsilon, then F and G are topologically conjugate. This is the definition of being C1 structurally stable. This example I showed you showed that these hyperbolic interval diffeomorphism, well, it does not prove it, but it shows you how it's likely that it is not C0 structurally stable. Okay, if it was C0 structurally stable, I would say that all the maps that are C0 close, epsilon close, they would be topologically conjugate, but that is not the case. Okay, so we just have 3 minutes left, so I will maybe just say a few words that the proof of the structural stability is actually fairly straightforward, and it's easy to see that if, for example, let's take this case here, which is representative, because in the general case, if F is hyperbolic, it will have a finite number of fixed points. And really, what you can do is you just take some neighborhood of this fixed point, right? And outside the neighborhood, so because of the theorem we've proved before, right, all we need to show is that as long as a diffeomorphism is C1, sufficiently close C1, then it is still hyperbolic. So all the fixed points have derivative less than 1, different from 1, and it has the same number of fixed points, right? So now if you take a neighborhood of all the fixed points, right, and you focus on this neighborhood, outside these neighborhoods, so this is the fixed point, so you look at the neighborhoods of the 3 fixed points here, right? Outside these neighborhoods, the map is far away from the diagonal, right? So in fact, as long as you take epsilon sufficiently close, there is no way you're going to change the number of fixed points. You're not going to do anything to the fixed points outside, right? So that's very easy. So really, you just need to concentrate in a small neighborhood of the fixed point, okay? And so the only argument is there. And then you need to show that in the neighborhood of the fixed point, if you look at this derivative here that is less than 1, that is different from 1, okay, then this means in a sufficiently small neighborhood that in all of this neighborhood, the derivative will be strictly different from 1, okay, either strictly less than 1 or strictly greater than 1, in this case strictly less than 1, and therefore in all these neighborhoods this is true, and therefore if the derivative is always less than 1, you simply cannot move back up and intersect the diagonal, right? On one side of this, you're crossing and you're below the diagonal, and if the derivative is always less than 1, you just cannot move back up to the diagonal, okay? So this is the heuristic argument. You can try. I think you should be able to do it, to actually prove it on your own. I will give you the notes that have the proof, so you can read the proof of this result. It's a nice result. So what we've done today in the context of interval diffeomorphism is a microcosm of 2 results, which we're not going to do in much. We're only going to do one other example of a class of systems where you construct this topological conjugacy, but this is an example of results in which for decades there was a lot of research going on, really trying to extend these results to higher dimensional systems, and this concept of hyperbolic diffeomorphism that we used in this interval case can be extended to higher dimensions, and in higher dimensions you need to introduce the notion of a uniformly hyperbolic diffeomorphism. We're not going to discuss this, but in the 1970s, this really was the beginning of a very important area of dynamical system, uniformly hyperbolic dynamics. And this was really motivated by the fundamental theorems that were proved in the 70s, which are exactly the generalizations of what we've done now, which is the fact that uniformly hyperbolic diffeomorphisms are C1 structurally stable, right? So this theorem, as it is stated, basically extends to higher dimensions in which you need to extend. The definition of hyperbolic becomes a little bit more complicated, but there is a big class of diffeomorphisms which have this property that when you perturb, you remain structurally stable. And this is, in these examples, you have more richness of dynamics, so you have more like the full branch map, so you have dense sets of periodic points, so it's much less trivial. In this case, the proof is relatively simple because you just have a finite number of fixed points. In the general case, it requires many more arguments, but the concept of the statement of the result is exactly the same. And the idea is that you want to study systems which remain inside the topological equivalence class. Okay, so thank you. And
Professor, I have a question on previous theorem, first theorem. Our first theorem says that about two functions, two C1 interval diffeomorphisms.
yes.
My question is why we require two function must be C1. Namely, I think it does not enough. We just require they are just homeomorphisms, they are just continuous functions. Namely, we require in the theorem both of functions are C1. Why we require?
You're correct, Milmokshin. Actually, the version of the theorem I stated was stronger than it needed to be. So if they're not C1, you need to be a little bit more. You need to include in the statement, the fact that the fixed points will be attracting or repelling. You need to say that you have a finite number of fixed points, right? So I simplified the statement of the theorem. If you say that the hyperbolic diffeomorphism, you automatically have a finite number of fixed points. You automatically alternate between contracting and repelling. But you're absolutely right. You can generalize this. And I think it would be a nice exercise, Milmokshin, to write down more general version in which you only assume it's a homeomorphism, but then you have to be a bit more careful, right? You need to say that you need to add the condition that you have a finite number of fixed points and that these fixed points are attracting or repelling. So you need to add a little bit more assumptions, but you're absolutely correct. That's a good observation. Thank you for the statement.
Okay, thank you for answering.
Sure. Okay. Thank you very much, everyone. See you on...
Professor.
Thank you.
Thank
Thank
you.
you.
See you on Thursday.
Bye.
Bye. Bye.